any questions on anything so far? There we go. All right. Okay, so here's what that looks like. So our NH3 has these 4 hybrid orbitals. And what we see is hydrogen covalently bonding right over here, 1, 2, and 3. And the reason I say this is a nice covalent bond is because I'm seeing this overlap. So last class we talked about how a covalent bond can be thought of as a direct overlap between the orbitals. And that's what they're showing here. So the purple are the hybridized orbitals, the blue are regular old s orbitals, and they're covalently bonded, which I know because of that overlap. All right, and then right underneath it we see the water, and the water we have the same situation right over here. We see that covalent bond coming from the overlap between the orbitals. So the hybrid orbitals act the same as an unhybridized would when we talk about a covalent bond. They have this nice overlap there. All right, any questions on anything so far? All right, so we talked about this. These are our instructions on how to figure out what the hybridization is. Now, right over here, there is a way to just memorize it. Some people feel more comfortable doing this. Some people say, hey, I'd like to just know that every linear is an SP, or you might have taken a similar class before where your teacher said, hey, just memorize it, and you absolutely can. If you don't like my method of the S, 3Ps, and 5Ds, you absolutely can memorize this. Every linear will be SP. Every trigonal planar will be SP2. And every tetrahedral will be SP3. So again, either method works. I think my method's a little easier because it's mine. No, I think it's easier because you don't have to memorize it. You don't have to figure out the geometry first. You simply count your electron clouds and then count the orbitals up that you need. But again, either method works perfectly fine. So any questions on anything so far? All right, so next up, more hybridized orbitals. So if you've watched the Lewis structure video, which I hope you have, you know that now we can have more than 8 electrons on our central atom. I see comments about people liking my method. Thank you. I find it a lot easier, and I've found over the years that most students do as well. All right, so you can have an expanded octet. So if you're in the 3rd row or below, you can have more than 8 electrons on your central atom. And that's what we're seeing right here. So let's go ahead and count this up. So around this phosphorus, I see 1, 2, 3, 4, 5 of our electron clouds or electron groups. So I'm going to list out our orbitals. So always 1s, always 3p's, and always 5d's. All right, so what do you think the hybridization on phosphorus is, knowing that we have 1, 2, 3, 4, 5 electron clouds or electron groups, and remembering that each one needs its own orbital? So what is our hybridization for that phosphorus? So I'll start you out with the S. There's going to be an S, and then excellent. So I'm seeing SP3, and then you can either say D or D1. Either one works. Both of those will work. Any questions on how we found that SP3D? Good question. So we have a question coming in about the lone pairs. Only lone pairs on the central atom count. If we were going to look at the fluorine, then we would count those lone pairs, but not on the phosphorus, because phosphorus has no lone pairs. And I remember there was a good question last class about would we ever look at the hybridization for an outer atom, and we are going to take a look at that today. But right now we're just focused on that phosphorus. But very good question. All right, other questions so far? Okay, so let's move on to this one right here. We have a sulfur with 4 fluorines. So what is the hybridization on the sulfur? Go ahead and take a moment. When you think you have it, go ahead and type in to the chat box. All right, excellent. So I'm seeing lots of people saying it is the same, and it is. It is sp3d. All right, so let's go over why. So I see 1, 2, 3, 4, and 5 electron groups or electron clouds. So that's why it is the sp3d. So just like the one on the left, 1, 2, 3, 4, and 5. We take the first 5. So any questions about why this SF4 is going to be sp3d hybridized? All right, so now let's move on to this one, and let's go ahead and do this one together. So I see, oops, grab a highlighter. I see 1, 2, 3, 4, and 5 electron groups. So just like the last two, I'm going to say the bromine is sp3d hybridized. So long as it has 5 electron groups, it will count as sp3d hybridized. Make sure you can see that 3 a little better. There we go. All right, so all of these have an electron geometry of trigonal bipyramidal. And anytime you do have an electron geometry of trigonal bipyramidal, it will always be sp3d. Now again, this is something you can memorize, but you don't have to. You can always count it up. So this is just for those of you who like to do flashcards and you prefer to memorize it. But again, I recommend just counting up those electron groups or electron clouds. So any questions on anything here? All right, so go ahead and try your hand at these right over here. You have your SF6, you have your ClF5 and XeF4. So if you haven't seen it before, it's a very kind of unusual compound, one that we didn't know could exist. It is a bond with a noble gas. So that's why we call them noble gases instead of inert gases. I've been telling you about how we have to change our definitions when we either discover something or we realize that two things don't match. When we used to call these inert gases, we thought, hey, there's no way that they could ever react with anything, and here's proof that that is not true. So xenon can react with fluorine, so no longer are they inert gases, but now we call them the noble gases. Just a fun fact. All right, so go ahead and find the hybridization on the central atom for each of these. And this over here is a lone pair. It's just got a little lip around there. All right, so I'm hearing it is sp3d2. Excellent. Yes, they are all sp3d2. Excellent. Any questions about why they're sp3d2? So all of these come from the electron geometry of the octahedral. So the octahedral has 6 electron groups or electron clouds around it. So it will always be sp3d2. And if we look at every one of these, we can count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, and 6. So all of them have 6 electron clouds. So they're all sp3d2. All right, so any questions on anything here about why these are all sp3d2? Oh, I see a question, does the number have to have a superscript or a subscript? Does the number have to have, do you mean that, does it need to be raised or lowered in terms of, because you're saying, so for these we do represent them as a superscript. Okay, so for these we do represent them as a superscript, but if you're asking about like the S, if there's only one of them, you don't have to put it. So you could have put S1, P3, D2, but this right here is optional. Oops. But if you're wondering about the 3 right here, that 3 does need to be there and it should be raised. It should look like an exponent. So it always should be above unless, did I do something that looked below? They should always be above. Maybe mine didn't look very clear. Let me try one more time. Yeah, they should all look like exponents. They should all be superscripts. Good question. So we don't really look at things that are going to need more orbitals than what we have laid out with the D's. So no, we're never going to include F's in the hybridization. However, if you get into geology, geochemistry, they have some huge molecules, and I have seen them with, let's see, 7, 8, 9. I think the most I've ever seen them with is with 9 groups. So I'm going to say even then I have not seen them hybridize orbitals, but they're the ones that really use the largest number of orbitals. But I'm not sure I've ever seen them even use the F. So definitely not in this class. The only time I could imagine seeing it would be a graduate level geochemistry class. But very good question. Oops. All right, so other questions on anything here? Oh, on the middle one, what is the symbol you circled? Oh, okay, great. So what I circled right there was just to show you that this is a lone pair, but in this particular drawing, they drew a circle around it, but it's not exactly a circle. So what it's showing is the area the lone pairs kind of can be in, and it's narrower as it gets closer to the chlorine here, and it'll get wider as it goes out. So it's not true that the lone pairs really have this circular area. It's more of an ellipse or even like a teardrop shape that they can travel in. So they're just trying to be more accurate with where the lone pairs can travel. I think I got all those questions. Any other questions? Okay. All right, so some fun right here, or hopefully fun. I want you to do the hybridization of all the central atoms. So go ahead and give this a shot. All right, so Clinton has a suggestion. What do y'all think? And Clinton, are you moving from, let's go ahead and number these. So if this one is number 1, Clinton, where's your number 2? Is it on the right here or on the bottom? Left to right and then top to bottom. Okay. 2, 3, and 4. All right. So what do y'all think? Oh, let's see. Jervin read it left to right, top to bottom. Is that how you read it as well, Clinton?
Professor.
Hey.
I was going 1, 2, 3, 4 like you have it written out.
Okay.
To the right and then down to 3. And
Okay, excellent. And then I see a question about double bonds, and double bonds do count as one. They're one electron group or cloud. All right, so how about everybody else? What do you think about the electron configuration? I'm sorry, not the electron configuration, the hybridization. All right, so we have a suggestion from Jessica as well. Excellent. Sorry, I'm finding it more distracting. It is more distracting at home than it would be in the classroom. All right, and let's see. Andrew is getting similar answers. Excellent. Anyone else want to be brave and go ahead and try typing in their hybridizations? So just in case you need more time but you're too shy to type it in, I'm going to go ahead and launch that poll. And you just Click in whether you want more time or you're ready to go over it. And it looks like Tasso typed in his configurations. Excellent. Okay, so it looks like everybody who is voting, oh no, there's one person who wants some more time, so let's go ahead and take another minute. It looks like we're having a disagreement on number 2. Some people are saying SP2, some people are saying SP3D. So while we're waiting, go ahead and take another look at number 2, and remember that double bonds do count as one electron group. So this is 1, this is 2, and this would be a third. All right, so let's go ahead and take a look at these. I'm going to start with number 2 because I think that was the one several of you got different answers on. So do we all agree that there's 3 electron groups? Okay. So with 3 electron groups, if we have our S, 3 Ps, and 5 Ds, I'm going to take the first 3, and this will be sp2. So any questions on number 2? I know that there were some people getting different answers. Was the problem with number 2 that double bond? Yes, okay, so it was a double bond that was confusing. So let's go ahead and go back to number 1. I just wanted to check in on number 2 because that was the one people were disagreeing on. But any questions on number 2 before we check in on the rest of them? Okay, so let's go back to number 1. So looking through the chat, it looks like the popular answer was sp3, and I agree. So it's sp3 because we have 1, 2, 3, 4 electron groups, and if we look at our first 4 of the orbitals, we have an S and 3 Ps there. So any questions on number 1 being sp3? All right, so let's move to our next one, and I see a popular answer of sp3, and I agree. This is also sp3 because we have 1, 2, 3, and 4 electron clouds. The fact that it has a positive charge does not change anything with hybridization. So that's an important point. So whether it's positive or negative or 2 plus or 2 minus, that doesn't change anything with hybridization. It's all about the electron groups. And I see a question about the brackets. So the brackets are whenever you do a Lewis structure and it has a charge, you always want to bracket it. So you're saying that that positive charge goes to the entire molecule. So the brackets are part of the Lewis structure, but again, that charge has nothing to do with the hybridization we're looking at. You're welcome. Any other questions? All right, so let's go take a look at what everybody was getting, or everyone brave enough to type in. And it looks like sp3d2 is the popular answer here, and I agree. So let's take a look at why. So we have 1, 2, 3, 4, and then we go to those lone pairs, 5 and 6. So it is the first 6 orbitals. So 1, 2, 3, 4, 5, 6. So sp3d2. All right. So any questions on how we found the hybridization for our central atoms? Okay. So I want to talk a little about bonding, and I have not forgotten my promise. I am going to show you a slide where we look at the hybridization for the outer atoms. Oops. I see a question about triple bond. So what was the question about the triple bond? Was it just about the hybridization of what it would look like in a triple bond? Oh, okay. So let's go ahead and take a look at something that's got triple bonds. So here, hydrocyanic acid would look something like so. So what would the hybridization around the carbon be? What would the hybridization around the carbon be? sp, excellent, because you only have 2 electron clouds around that carbon. Excellent. So any questions on why it is sp? And I see some 1s, and you're always welcome to say S1, P1 if you prefer. You're welcome. Any other questions here? Okay. All right. So next we're going to move on to the idea of sigma bonds. And what I didn't tell you is when I said direct overlap, that handshake, that is specifically a sigma bond. So here, sigma bonds, we say they lie along the internuclear axis, which is a really scary word to say that the electrons are between the 2 nuclei. So if I have my 2 s orbitals and they're overlapping here, we say that the bond truly exists right between, grab another color here, right between the 2 nuclei. That is the internuclear axis. I think that's a very confusing word, so I'm going to promise you I'm never going to put that as a vocab word on a test. But in case you see it further on in your chemistry or other science careers, internuclear axis is just right between the nuclei. And that's actually why we draw our bonds like so. We're actually drawing that internuclear axis. So it's an imaginary line that connects the 2 nuclei. So they result from that direct overlap of orbitals. So all single bonds are sigma bonds. And you're going to see as we go through that I'll refer to sigma bonds with the symbol for sigma. And I know that wasn't the most beautiful sigma in the world, but this sigma right here, that's how we will be referring to these direct overlap bonds. So any questions so far about that sigma bond? What do you mean by the node for the sigma bond?
Sorry, I typed slow.
Oh, no problem, no problem.
I just remembering back a few classes ago, I just remember that the electron couldn't be in the node.
Yes.
Um,
So if you're are you thinking about the s orbital nodes?
yes.
Okay.
Yes.
So let's kind of think about where the electrons would be inside of here. I'm going to draw in some nodes as best I can. There we go. All right. So let's think about this one as being, so here is the 1s, here's going to be my 2s, and this is going to be my 3s here. Oops, 3. And now I'm going to have another one of these same atoms. And now what I'm going to do is I'm going to bring them together here. Now the nodes are still the nodes. No electron should be in the node, and I think Andrew made a comment like that on the chat. There still should be no electrons there, but what we can see, and we actually get a good view of it as we bring in the second atom, is that as they start overlapping, if you can see how it gets darker there, that's showing an increased probability. It just coincidentally shows an increased probability. So we're now more likely to see our electrons. Oops, let me get a thinner one. Right in here, here, and here. But notice the nodes should still be nodes. There still shouldn't be any electrons in there.
Okay, so it's not like a direct line straight across where the electrons flow. It's still
yeah.
Okay.
It's kind of, I guess you could think of it more as a dashed line if you wanted. So you're thinking of the internuclear axis. So still kind of
Right.
Yeah, you still kind of have to avoid those nodes as best possible. Yeah.
Got it. Okay. Sorry.
Oh, no worries, no worries. It's a good question. All right, other questions so far? This is actually a great way to learn when you're making connections to other chapters. It helps you remember the previous chapter and have some foundation for the one you're working on. And as we're only a few weeks away from the final, it helps you as you're getting ready to study for that final. All right, so here are our sigma bonds, and this hydrogen got cut off a little bit. So the hydrogens come together, and they form H2. So here what we have represented is the two electrons directly in that overlap region. But what we know in reality is they kind of go everywhere. They're just going to spend more time between the two nuclei than outside because they're attracted to both of the nuclei. They're attracted to both of the positive charges. So down at the bottom we see the same thing just shown in a slightly different image. So when we think about where those electrons would be, if we had only one hydrogen, we'd think of it sort of in this sphere, and I know it looks like a circle, but imagine it to be a three-dimensional sphere or ball. And when they get together, we kind of imagine them to travel around here, but spending most of their time right in here. And this is actually shown with this dotted line. So they should be right between the nuclei, but again, always avoiding the nodes. So any questions so far about this idea of the sigma bond and it's formed by that direct overlap? And I keep doing this for a reason, and that's because we're going to get to a different kind of bonding that doesn't do that in a little bit. But one thing that I'm going to be emphasizing is sigma bonds are extremely strong because it's like shaking hands. They are grabbing onto each other in the middle, if you will. So that forms that very strong sigma bond, the strongest type of bond we have. So we took a look before on overlap, and I showed you how two p orbitals might overlap. And here they are right here. So the orbital from one of the fluorines is right here, and another one right here. So this image shows the two electrons right in this area here. They don't necessarily need to stay there. That's just showing that that's where we see more electron density, because that's where they're going to spend the majority of their time in that overlap area. And here we see our sigma bonds with the hybrid orbitals. So here is a hybrid orbital. Here's a regular old s orbital. And this is the sigma bond right here. And we see that for each of these. We also see something interesting that we don't see too often here. And that is the little tail of the whale, if you would. That is that end of the hybrid orbital. So remember, hybrid orbitals look something like so. It is this tail right here that you're seeing right over there. Usually we leave it out just for clarity, but in this image they actually show it to you. So that's what you're seeing with these little ends right here. Okay. But any questions so far about our sigma bond? All right, so moving on to our multiple bonds. So every multiple bond must have a sigma. That is the core, that's kind of the skeleton is how I like to think of it. But then we start adding what we call pi bonds. And pi bonds are different because they're going to be a sideways overlap, always from unhybridized p orbitals. So here it says 2p orbitals. I'm going to make a note and say these are unhybridized. And again, the pi bond can only happen between unhybridized orbitals. So in other words, when you were hybridizing things, let me go way back over here. And let's say you didn't use all of your p orbitals, like here we have a spare p orbital. It is now available for a pi bond, but it has to be a p that you didn't use before. All right, so the way this is going to work is if you have a p orbital on one atom and a p orbital on another atom, they're going to share electrons across. So sometimes we think of it as a linking of arms rather than a handshake. But this is a much weaker type of bond, and this is why when we have a double bond, it is not just twice the strength of a single bond. Because the double bond always has a sigma in the middle and then a pi. And what you'll be seeing in the images coming up is the pi has two lobes. Because the p orbital has two lobes, so does the pi bond. So even though it kind of looks like, and I did just draw two highlights coming across, that's all part of the same bond. So just like electrons can jump from the bottom to the top, the electrons can jump from the lower lobe of the pi bond to the upper lobe, because that's all one pi bond. So I'm going to be showing you some real graphically designed images. But any questions on anything here so far about how those electrons are going between the unhybridized p orbitals? Okay. So again, it's a sideways overlap between the two unhybridized p orbitals. And in this image, all the sigma bonds are drawn in black just so we can focus on the pi bond. And the pi bond, to me, it looks like a bubblegum pink, and you notice it's stretched between the two p orbitals. And again, we have down here that it is two lobes. Two lobes of one pi bond. So one bond that has a top and a bottom to it, if you will. Now, one thing that you're going to learn if you go on to organic is that there are things called electrophiles, and if you were going to dream up a story about chemistry, and if I told you that one of my friends when I was a student, she decided she liked chemistry, but not quite that much, so after she graduated, she started doing children's books about chemistry, and I see, is there a pi bond between hydrogen and carbon too? No, here just between the two carbons, because you only get a pi bond if it's a double or triple bond. So let me draw the structure for you. So this is going to look something like so. So the only time you have a pi bond is if you have a double or triple bond. If it's a single bond, it's always a sigma bond. And good question. In this case, yes, this is a flat molecule. So not all molecules are flat, but this one, it is, and that's what they're showing you. Oops, I didn't draw a good job. I didn't do a good job outlining it, but that's what the blue box is here. They are showing you a flat plane. Yes, exactly. Okay. So just to mention, those of you going on to organic, you are going to see those electrophiles. And if you were going to do, if you were going to write a story about chemistry, electrophiles would be sort of the bad guy. They're going to go around, they're going to steal electrons that don't belong to them. These pi electrons are very susceptible to being stolen. And so the reason they're susceptible to being stolen is they're far away from the nucleus. So here is that nucleus right over here. And the nucleus does a very good job of controlling the sigma electrons. So if you think of the nucleus as that parent that is going to control where the kids go, who their friends are, they do a much better job with the sigma electrons. With the pi electrons, they have gone quite a ways away from home, so they can't really control their friends anymore. And what another way of saying that is that those electrophiles are much more likely to steal electrons from a pi bond, and that is part of what makes it a weaker bond. as those electrons drift from the nucleus, they don't have as much attraction to that center, to that nucleus, and now they can get stolen very easily. And when I say stolen, I also mean the bond will break. As soon as they get stolen, boom, that pi bond breaks. So that's part of what makes this a much weaker bond than the sigma. And then I see a question about whether it's common to have a flat molecule. If you have a double bond, it is. So what, we didn't really talk about it when we did the organic, but just to kind of give you an idea, when we had our single bonded molecules, these all actually take on a tetrahedral shape when you factor in the hydrogens. But if you had a double bonded molecule, that is going to be a nice flat molecule. So the double bonds do predict that at least in the area the double bond is going to be in, that is flat. And it's very common. Actually, what I just drew is called a conjugated double bond, and that's extremely common, especially in our food. So highly colored food generally has a conjugated double bond, which then makes it a flat molecule, yes. So long as we have these double bonds, wherever those double bonds go, that part of the molecule is going to be flat. When we have just a single bond, that part of the molecule is usually a tetrahedral. Hybridization only occur when there is a central atom. So let's see. So if I had something like so, I could still talk about hybridization. I guess the one time we wouldn't talk about it is with something like hydrogen, because hydrogen, hydrogen only has the one bond. So that's the one time we wouldn't talk about hybridization, but pretty much any other element we can always talk about hybridization. We normally only care about it for the central atom, but we could talk about it for every atom. So for instance, if I wanted to do, let's say, CH3, CH2, like so, I could talk about the hybridization for anything except for hydrogen. And just for the fun of it, if I was looking at this carbon right here, what do you guys think the hybridization would be? sp3, excellent. All right, and so the carbon I just drew an arrow to, this one right here, if you have to guess, what is the hybridization? All right, so I'm seeing sp2, which is correct because we got 1, 2, 3. And this carbon right over there, what's its hybridization? Excellent. And actually, when you get into organic chemistry, they are going to want you to recognize the hybridization right away. So as soon as you see single bonds all around, you're going to say, hey, that's sp3 because single bonds all around. If you see all single except for one double, you're going to be like, hey, that's an sp2. And if you see a single and a triple, you're going to be like, hey, that's an sp. So you'll learn to recognize those when you get to organic. And I think I probably went way beyond the question, but good. Sorry about that. Going off on a tangent. I know students hate it when teachers go off on a tangent too much. All right, so on that note, I think it is time for break. So let's go ahead and come back at 6:10. All right, so any questions about what I was talking about before we went on break with regard to the double bonds, the pi bonds, or anything like that? All right, so here it says, what is the hybridization of the carbon orbitals in C2H4? So whenever we're doing something like that, I always find it most helpful to go back to the Lewis structure. So let's go ahead and do our Lewis structure, and it is a nice flat Lewis structure. So what do you think the hybridization on that carbon is, the one I just drew an arrow to? So I see Clinton suggesting sp2, and it looks like Nino agrees. How about the rest of you? Excellent. All right, so I agree it is an sp2 because we have 1, 2, 3 electron groups around that carbon. So any questions on why we would call that an sp2? All right, so on the other side, I'm also going to call it an sp2 because it has 1, 2, 3 electron groups around it. So any questions on how we'd identify the hybridization on those carbons? By the way, on a test or quiz, I would never give you a picture like this to identify hybridization. I would always give you the Lewis structure because I think it's too difficult to look at that colored image and kind of sort everything out. All right, so now we're looking at formaldehyde. It is the same formaldehyde you might have smelled in biology once upon a time if you did dissection. So this is CH2O. So again, we have our pi bonds in the pink. So those pi bonds are up here and below. So they're on the top and the bottom. And we have our hybrid orbitals in purple here, 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 and here. And the sigma bonds are going to be the overlap between the hydrogen and that purple hybridized orbital. All right, but what we're going to focus on in this slide is the sigma and the pi bonds between the carbon and the oxygen. So if I were to look at the carbon here and the oxygen, I see one sigma bond between them. And there will always be one and only one sigma bond between any two atoms. So no matter where you are, which molecule, between any two atoms, you always have one and only one sigma bond. Next up, I see one pi bond, and again, it looks like it has two, but it is one bond with two lobes. Another way to look at this, and again, I'm going to go back to the Lewis structure because I think it's easier to see it there. And I'm going to go ahead and I will use purple for the sigma bonds. You always have a sigma bond between any two atoms. If it's a single bond, that's all you've got. So think of it as the skeleton that has to be there. And I'm just going to choose the bottom one here as my sigma bond. As you know, it's really here in the middle, but I went ahead and just chose it to be the bottom one. Now I'm going to use the green to highlight the other bond, and I'm going to call the green my pi. Sorry, it wasn't a great pi. There we go. Anyways, so anytime you have a single bond, it is always one sigma. Anytime you have a double bond, one sigma, one pi. So any questions on anything here so far? So here they're asking for the hybridization of the carbon orbitals, but I'm also going to ask you for the hybridization of the oxygen. So let's draw this out again. And I want you to find the hybridization on the carbon and also the hybridization on the oxygen. When you have an answer for these, go ahead and type these into the chat box. We're looking for the hybridization on the carbon and the hybridization on the oxygen. All right, so I see sp2 coming through. Excellent. All right, and I agree with you. They are both sp2 hybridized. So if I look at the carbon, 1, 2, 3 electron groups. And if I look at the oxygen, 1, 2, and 3 electron groups. So whether your atom's in the center or whether it's on the outside, you can check the hybridization either way. So any questions on anything here? So just to briefly talk about an application of this hybridization and these sp2s. And again, this is just some fun facts. So you've probably heard of carbon monoxide poisoning. And carbon monoxide looks like so. And oxygen that we are supposed to be inhaling actually looks like so. So it's the oxygen that actually attaches to the iron in your blood. So your blood has something called a porphyrin ring. And at the very center, sort of the jewel of that ring, is the iron where the oxygen is going to attach. And if I look right over here, there are only 2 electron groups around the oxygen, so I'm going to call that sp. And if I look right over here, there are 3 electron groups, so I'm going to call that sp3. So what happens is you have a ring, and I'll draw it as a circular ring, although it's really kind of a jagged ring, and in the center has the iron, and the oxygen in either O2 or carbon monoxide flies up into this. And when the CO2 flies in, what we see is a nice direct connection because we have a linear molecule based on the sp2 hybrid orbitals. But for the O2, we actually have kind of a sideways bond. Because this is an sp3 molecule. So the O2 is not bonded as directly or as firmly as the carbon monoxide. And so what that allows our body to do is to take in this O2 and give it off very easily. So up near your lungs, the O2 floats into that iron, and then when it gets into the muscles, gets into the tissues, it kicks off, no problem. But because this over here is sp hybridized, it has that direct connection, the CO cannot release, or I should say it doesn't release very easily, so it might stick to that iron for up to 7 hours. And that's how carbon monoxide poisoning works, because if you're getting it at home, then you go out to work, you may not have lost all of it by the time you come back. So it's all because of the structure based on those hybrid orbitals, this one being an sp and this one being an sp, oops, not sp3, sp2. Sorry about that, sp2, there you go. So just a little application, but again, this is just kind of a side note. You do not need this for the test. Okay. Any questions here? So I find biochemistry to be extremely interesting. It helps you to relate what you do in the chemistry class to what's actually going on in your body. So I think one of my favorite, or probably my favorite non-chemistry class was physiology, where I got to learn all those connections in school. And interestingly, I just took it as my GE because I didn't want to take biology because I didn't want to do dissection in undergrad, so instead I took the physiology class. All right. Questions about anything we've been doing so far? All right, so now we're going to move on to our triple bonds. And our triple bonds always consist of 1 sigma bond and 2 pi bonds. Now, I'm going to show you a picture, and it's way beyond my artwork abilities to draw that kind of a picture here. But what I'm going to draw you is a picture that will help you remember it. So this is a Lewis structure, and I believe we used purple for our sigma bonds. So I'm going to go ahead and color sigma in purple. And so what you're seeing here is anytime you have 2 atoms connected, there is always a sigma bond. Think of it as the spine. Without your spine without your skeleton, you would be nothing. You would just fall as a pile of goo. So we need a sigma bond for that connection. These two atoms would float apart if they didn't have that sigma bond. But anytime you have a multiple bond, whether it's a double or a triple, all of those extra bonds beyond the sigma, they must all be pi. So I kind of like this drawing just because it helps me to remember what's going on, and it helps me to remember that there must be a sigma bond between any two atoms, but it can only be one sigma bond. So one and only one sigma bond, everything else has to be a pi bond. Okay, so I'm going to go on to some of the computer-generated images, but any questions here? All right, so here is acetylene. So acetylene has a triple bond. It's the molecule I just drew for you on the other page. And why this is tough for those of us who are not artistically inclined is because you really have to have the 3 dimensions here. So I can trace, that I can do. So what I'm putting in blue right now, this is one p orbital. It's got a top and a bottom, just like all our p orbitals. And it's going to match up with one on the other side. Okay, so the one that is on the top and the bottom, those two are going to share electrons, sideways overlap, very vulnerable to an attack by an electrophile, but that is part of it. And that's one pi bond. I just drew it in blue there, the top and the bottom you're seeing. And I'm going to go ahead and use a lighter color. So now there is another orbital. So here in the back, and also in the front. So once upon a time when we talked about our p orbitals, we said it was px, py, and pz. So 3 identical orbitals, but they lie on different planes. So what you're seeing here is in the blue, you're seeing one of the p orbitals, and in the green, you're seeing a different p orbital. So again, these are supposed to be showing perspective, where you see part of it going away from you and part of it coming out towards you. So now the green ones are going to share electrons as well. So they're sharing electrons in the back, and they're sharing electrons in the front. So if you were an electron, if you remember way back from our quantum number days, you had a -1, a 0, and a +1, you would be assigned to one of the 3 orbitals. So if we go ahead and call this our -1, if you were assigned here, you get to be here, you get to be here, you get to be here, or up, or down. So that's where you get to be. Now let's say you are in the 0, then you could be here, or you could be here, or you could be back here, or over here, or in front, or behind. In order for this green one to get into the blue, it actually has to jump orbitals. So it would jump over, and in this case it would have to flip over as well. Like so. So we said that is possible, but it's very destabilizing for the element. So most of the time they should stay where they belong in their own respective pi bonds. So again, if you're an electron assigned to one of these pi bonds, for the most part you are going to stay in that pi bond. But still, don't feel bad for them because they have a lot of places to go. So this one in the blue could be here, 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 down here, or up there. So they got lots of traveling they can still do. All right, but questions on anything there? Hopefully you don't mind my throwback to the quantum number days. All right, so here it says how many sigma and how many pi are going to be in each. So I want you to take a minute, kind of fill in these blanks, identify how many sigma bonds and how many pi bonds in each. For this one right here, I'm going to say total. So I want you to identify the total number of sigma and the total number of pi in the molecule. Or actually, let me do one more thing first. Hold on. I'll have you do this one between carbons only, and then we're going to do it one more time. And I'll have you do total. So this time you're counting up the whole molecule, all sigmas and all pi's. So we got 4 of them to do, so go ahead and give these a shot. And I just saw your note, Tasso, something about attraction. So you want to tell me what that one was about? I must have missed it. Was that about the iron and the oxygen or the carbon monoxide? Yes. So in terms of how attracted they are to the iron? So both of those oxygens are very attracted to the iron. I don't know if the oxygen on carbon monoxide is really any more attracted, but because of the orientation based on those hybrid orbitals, it gets a nice secure connection, and that's why it does not float back off the same way that the O2 would float off, and that's why it can build up in your body and cause the carbon monoxide poisoning. And I will restrain myself from telling you the story about a story I have about carbon monoxide poisoning. Yes, it can be very dangerous. All right. Excellent. So I got a few of you who have some good ideas. So let me go ahead and put up our poll. All right. So go ahead and click in if you would like more time or you're ready to go over it. Now I have to tell the story. Oops. Oh, I'm sorry. Now go ahead and click in. So I'll tell the story for those of you who are done and need something to do while you're waiting. And that is, I had a landlord when I was living in Indiana. I was going to Notre Dame, and it was my first time living in the snow, and I didn't realize they had those big heaters. And I asked the landlord about carbon monoxide poisoning. He's like, yeah, you know, when my wife and I were first married, we moved into this place, and you know, we started arguing a lot, and we were getting along, and I just figured, you know, we're newlyweds. That's the way it's supposed to be. And then after a while, we noticed we were both getting kind of pink in the cheeks, and that's when we realized, hey, it might be carbon monoxide poisoning, and they got that taken care of, and then they had a very happy marriage after that. All right, so it looks like some of you need a little bit more time, so go ahead and take another minute or so, and then we will go over it together. There might be more to the story, but that's all he told me about. Happily ever after the carbon monoxide poisoning was taken care of, I hope. But it's true, every once in a while I'm like, wow, I've been having a really bad day. I just seem to be getting upset about everything in traffic. Is there any carbon monoxide around? All right, so how's everybody doing? Would anybody like a little bit more time for these? All right. So let's go ahead and go over these, and I'm going to go ahead and color these just so we kind of have an idea of what we're talking about. So again, I'm going to make my sigma in the purple, and I will go ahead and make the pi in the green. So for the first one, all we have is that sigma. So I'm saying 1 sigma and 0 pi's. So any questions about how that hydrogen molecule has only 1 sigma and no pi's? All right, so next molecule, we're first going to look only between the carbons. And I'm going to say I have 1 sigma 1 pi. So any questions on how we did that second one? All right. So then we're going to look at this N2, and we have 1 sigma, and both of the other ones are pi. So remember, between any two atoms, you can only have 1 sigma, the rest are pi. So it's looking something like so. So any questions on the first 3? All right, so now the last one is the tougher one, but I do want you to be able to count sigma and pi in a full molecule. So here is a sigma, 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 and then there's one of these that's going to be our sigma. The other one would be a pi. All right, so it looks like we have 1, 2, 3, 4, 5 sigma and 1 pi. So any questions on anything here? All right, just for fun, let's do another one where we have a big molecule and we're going to count everything up. I say just for fun because I think this is a lot of fun, but I apologize if for those of you who are sitting there like, oh my god, another one? These are horrible. Hopefully they're not too horrible. All right. So I'm going to draw this out, and at the end I'm going to ask you to try to figure out how many sigma and how many pi. Just for fun, I'm going to throw in an oxygen. There we go. All right, so go ahead and take a moment and try to do the total number of sigma and the total number of pi in here. All right, so it looks like Clinton's suggesting 16 sigma and 4 pi, and it looks like Jervin got a similar count. Excellent. All right, looks like Tassa's getting a similar number. So keep on working on that. For those of you who feel comfortable with your number, try to figure out what that functional group is. Don't forget we did functional groups way back in the beginning of the semester. That'll all be coming back for the final. So give that a shot. All right, excellent. So Clinton's suggesting a carboxylic acid. So those of you who've already got your counts, anybody want to chime in and see if you agree with Clinton? All right, so go ahead and click in if you'd like more time or if you are ready to go over this. All right, so it looks like there's a few people who want some more time, so let's go ahead and take another minute or two. Those of you who agree with Clinton, don't leave him hanging. You can private message him if you want, or you can put it on the general chat board. A private message is just using the drop-down menu where it says to and then choosing who you want to respond to. All right, so Andrew is agreeing with Clinton. Excellent. So let's go ahead and give this a shot. All right, so I'm going to go ahead and highlight our sigma bonds first. So here looks like we have 1, 2, 3, 4, and I'm going to highlight just one of these, and that makes 5, 6, 7, 8, 9, 10. Just one, that'll make 11, 12. Just one of these, and I believe we're at 13 now, 14, and 15. And let's see, did I miscount? Let me try it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I did miscount. All right, so it looks like we were at 16 for our sigma bonds. Any questions on how we got those sigma bonds? All right, so now let's try our pi bonds. I'm going to zoom in, and that's a pi bond. So there's 1, 2, and 3, because we have 2 of the pi bonds inside of a triple bond. So 3, and here is going to be our 4th one. So it looks like we have 4 of the pi bonds. So any questions on how we did our counts? All right, and then looks like Andrew and Clinton were the only brave ones regarding this functional group. So this is indeed a carboxylic acid. I shouldn't have said they're the only brave ones. Everybody else is brave in their own special way. But our carboxylic acids look something like so. And over here it was some kind of an R group, basically the rest of your molecule. All right, so questions about anything we've done here with counting sigmas or pi's? And any questions about how the carboxylic acid? Oh, was it really that bad, Tasso? Okay, good. Could be worse. I could be giving you another lattice energy calculation. By the way, for those of you who feel like you scary at first, yes, it is. When you see something that big, it is very scary, especially because we haven't dealt with molecules that big before. Yes, I agree. For those of you who are thinking you'd like more practice on lattice energy, if you go into the homework section and then you scroll down to recommended homework, there is a worksheet that has another one, and that one does have an answer key up in the answer key section, so just in case you wanted to do that. All right. Next up, we're going to talk about localized versus delocalized bonding. So local means it is the chemical bond is trapped between 2 atoms, and this is the way we've always thought about it. So if I said that I have a hydrogen-hydrogen bond, you think of the electrons here being trapped between those 2 hydrogens, and that is what we call localized. So that's everything we've done so far. So electrons are shared only between 2 atoms. They aren't passed around like party favors. They belong to those 2 atoms. Then we come into our molecules that have resonance, like benzene. And so what we see is that we could have the double bonds in the locations that they're here, or they could move over here. But we've said that neither of those are the true structure of benzene. The true structure of benzene has electrons that can actually travel. So these electrons can actually travel, and they do actually travel in sort of a circular pattern, and we can influence those with a magnet. But the idea is they are not trapped. They are not like the electrons that are trapped between these 2 hydrogens, and they really have nowhere else. It's not like they can call their aunt and uncle and be like, Mom and Dad are being mean, I want to come over for a while. Whereas the electrons here, they can travel around. When they get sick of one carbon, they go off to another one. So they are free to travel. Now, when we talk about something being localized, again, we're saying that they're trapped between 2 different atoms. And that's what you're seeing in these pictures here. All right, so here, these are representing what we call localized bonds. These are saying, well, the electrons are trapped here, or they could be trapped over here. And that's what this represents down at the bottom. That's what the resonance structure represents. It represents localization. But localization is not true for a structure that has resonance. If it has resonance, it is not truly localized. It is truly delocalized. And that's why we draw our benzene with a circle in the middle to represent the fact that those electrons can travel. So we say that there's a sea of electrons that can travel. They can travel above or below the plane of the molecule. So they can travel up here above or down here below. And that goes back to the fact that every p orbital has two lobes. So if you think of the top one as being above the ring and the bottom one as being below, then these electrons can travel anywhere in the top ring, or they can jump down and travel anywhere below as well. So it is considered delocalized because the electrons are shared between more than two atoms. In this case, all 6 carbons get to share these electrons. So any questions about the idea of the delocalized bonding? This is something we're going to see for all of our molecules that have resonance structures. All right, so here we're looking at benzene again, and here we've actually separated out the sigma from the pi just so it's easier to see things. So when we're looking at the sigma are always localized. So let me zoom in here. To have this direct overlap, it's got to stay right where it's at. These electrons cannot travel to any other location. The only electrons that can travel will be pi electrons. Those are electrons involved in a pi bond. And here is where they can go on the top. They can visit any of those carbons, and they can also go around the bottom. So any questions, again, between the difference between localized or delocalized? All right, so just one more time, your sigma, let me actually write this out just so you have it in writing here. So your sigma bonds, here we always have and now what we're going to say for our pi bonds, if there is resonance, then they will be delocalized. But that can only happen for the pi electrons, the electrons involved in that pi bond. So any questions on anything here? Anyone need a minute to write that down? Yes, okay. Go ahead and take a minute or two to write that down. Any questions about anything so far? Excellent. Would anybody else like some more time on this slide? All right, so here we're looking again at that delocalized bonding in benzene. And just as a reminder, it's been a while since we did those skeleton structures. Whenever you're looking at a skeleton structure, the vertices represent the carbons. Those are the little bends right here. And the hydrogens are not shown. They're just assumed to be there. And then a circle represents the delocalized bonding. So the circle representing delocalized bonding is specific to benzene. Other molecules, they may not be delocalized in a circle, so they may not be shown as a circle. So in this particular molecule, this circle right here is representing the delocalization. And if you look in journals, chemistry, biology, medical journals, you're frequently going to see the benzene with that circle, just showing that delocalization. All right, so here's our nitrate. So does it have delocalized bonding? What do you think? All right, so I'm seeing a yes from Jervin. How about the rest of you? Excellent. Excellent. So it has delocalized bonding, and the reason is because it has resonance. But just looking at it, how do you know it has resonance? Okay. So some of you guessed on it, and then I see the double bond that could be anywhere. That's exactly right. That double bond does not have to be on the top. It could have been with any of those 3 oxygens. So if this was a test or quiz, I would want you to draw all 3 possibilities. All right, so here, the double bond was first located on the top, but we could have put it on the left, or we could have put it on the right. And once upon, I think, a time, and I think someone brought up the idea of the hybrid model, because one of your previous teachers drew it in the hybrid model. And what that model is actually showing is the delocalization. Those electrons from the pi bond could travel anywhere throughout this NO3 minus molecule. So any questions on anything here so far? So here's what it looks like with this computer, I want to say computer animation, but it's a computer rendering. So the electrons have the ability to travel anywhere along this top area or anywhere along the bottom area. So again, all of these p orbitals have 2 lobes. So they can travel along the top lobes, which would be these right over here, or they can jump down to the lower lobes and they can go through here. So these electrons can go anywhere they want. If we apply a magnet, then we can force them to go one way or the other, but without a magnet, they can go anywhere they want, and they just kind of average around to be just about everywhere. There's no necessarily preferred atom unless there's something very electronegative or unless there is a magnet applied. But again, delocalization refers to any time the electrons can travel between more than 2 atoms, and that's going to be anytime you have resonance. So any questions about localized versus delocalized bonding? All right, so why don't we take our next break now? When we come back, we're going to do molecular orbital theory, which is not as scary as it sounds, I promise. So let's go ahead and come back at 7 o'clock, and we'll have lecture for about another hour or so. All right, so let's go ahead and get started again. Any questions about what we were talking about before break? All right, so we're going to start talking about what we call molecular orbitals, or molecular orbital theory, which we often refer to as just MO theory. So it helps us to understand what a molecule looks like, So thus far, when we do things like our orbital diagrams, we've always talked about individual atoms. So what's the electron configuration of an atom? What is the quantum numbers for the electrons in that atom? It's all been centered around individual atoms. Now we expand to molecules, and for us, we're only going to be putting 2 atoms into the molecules that we do here for the MO theory. But in the greater scheme of the world, you could put any number of atoms in there. So here, the MO theory can help us to see what it's going to look like. It's going to help us to draw the MO diagram. It can also help us to predict things like the diamagnetism and paramagnetism for a molecule rather than an atom. So we'll be reviewing that and again looking at what it's like for the molecule as a whole. So we're going to start off with hydrogen gas, just H2. And that comes from combining 2 individual hydrogen atoms. So if we were to do the electron configuration for a hydrogen, it would be 1s1. And if we were to do the orbital diagram, it would look something like so. All right, but now we have 2 of those hydrogens, so I'm going to do the same thing over here and the same thing right over here. So the idea is we're taking 2 individual hydrogens and we're going to combine them. All right, so here is the individual hydrogen atom, and I'm going to put my 1 electron in there. Here's my other hydrogen atom, and then putting my 1 electron in there. So thus far, I've just been looking at what happens for the individual atoms, but inside the middle part, and the middle part is a really important part. So whenever I ask you to draw, say, an MO diagram, the only part that I care about would be the middle part. So that is to say that I would only require you to do the middle part because this is the true MO diagram. So what we're going to do is we are going to combine those electrons. So if I count them, I've got 1, 2 electrons. Now we're going to fill up this MO diagram, always starting at the bottom and then moving to the top. Now we're going to use the same rules we used for electrons before. Sorry, I'm trying to find the right spot for the microphone. Okay, so we're always going to use the same rules that we used for our orbital diagrams before. And the first rule is we fill up 1 before we go to the next energy level. And if we ever have 2 electrons in the same orbital, they have to be of opposite spins, which we represent as arrow up and arrow down. So I've got my 2, and I'm going to put them right here. So I must fill up this one before I move to the next one. And when these are in here together, we must have an arrow up and an arrow down. We can never put 2 up or put 2 down. So an arrow up and an arrow down, and we have to complete that one before we move up to the one above. So I want to talk about this one a little bit more, but any questions about what we've done so far? So another way to approach this would be to count the electrons, and I'm going to encourage you to count the valence electrons. So this is similar to doing a Lewis structure. Hydrogen has 1, the other hydrogen also has 1, for a total of 2 valence electrons. And then you start loading your electrons into the bottom of the MO diagram. By the way, I will give you the MO diagrams. So you're going to start loading them into the bottom, and you're going to make your way up to the top. So any questions on anything so far? Let's see. So why are there 2 1s boxes? So you mean this one and then this one up here, right? Yes, so that's what we're going to talk about next. Excellent question. And then you don't need the stuff outside the rectangle. Technically, no. All I need you to do is the stuff inside the rectangle. Some people like to do the outside as well. You'll see their textbook does the outside. But again, for me, all you have to do is inside that black rectangle. All right, so next up, let's get to those 2 1s's. So down at the bottom, there is a sigma. So remember, the sigma is that direct overlap. It's kind of the skeleton of the molecule. And it comes from the 1s orbital. So there's an overlap between the 1s's from hydrogen, and that's how we make this sigma 1f. But I've told you before that whenever we have two orbitals that are combining, we always get two out. So that means we need two types of the sigma 1s. They are both direct overlaps. They both came from the 1s because each hydrogen ion, or I'm sorry, each hydrogen atom was a 1s1. But they're different. You can see they're different energy levels. One is a lower energy level, it's favorable. One is a higher energy level, and it's unfavorable. And that unfavorable one has a little star right here. And that star represents it as being what we call an antibond. Back when I was younger, we thought we were really cool because there was an anti-mall. It was still a place that self-closed, but they were an outdoor mall, but they thought they were cooler, so they called themselves the anti-mall. I think it still exists somewhere in Orange County. But this here is an anti-bond. And so what the anti-bond does is it actually destroys the chemical bond. So I've been telling you about the villains of chemistry today, about the electrophiles. Here's another one, the anti-bond, which breaks up your chemical bond. So the idea is when you put electrons into an antibond, you are effectively breaking the bond that came before it. And we're going to look at that a little bit more. But in terms of these structures, and again, I said that I would give you these structures, I will always, trying to find the right spot there, okay. I will always mark the antibond with that star, and sometimes we just refer to this as sigma star. And sigma star means the sigma antibond. But there is an antibond for pi's as well. So we will see sigma antibonds and we'll see pi antibonds. So, any questions so far? And I'm going to talk more about the antibonds, but any questions so far? See if I can get this into a stable place. Okay. All right, so here is the sigma bond and the sigma antibond. So the sigma bond is formed from the 1s orbitals, and it is a bonding molecular orbitals. When you put electrons in there, you're forming a chemical bond. Then the anti-bonding is the opposite. When you put electrons in there, you are destroying the chemical bond. And I apologize, let me grab the cat for a second. Karma, my 16-year-old kitty, likes to try to steal the food from the other cat, and she is on a special diet for her kidneys, and she's not supposed to have the tasty food. All right. So questions so far about the bonding orbital, the sigma 1s, and the anti-bonding sigma star 1s? I can only imagine how rough it is to live with another cat that gets food that tastes better and smells better than yours. All right. So here's an idea of what these look like. And I mentioned additive and subtractive combinations once before when we were doing our hybrid orbitals. And I mentioned that they come from the idea that the wave function has signs, not charges, but signs. And if those signs are the same, they add together, everything goes well, we get nice bonding electrons. However, if they are of different sign, when we combine them, we actually get a node in the middle. And that node is the area of zero electron density. So what it's saying is there should be no electrons between the two nuclei. So when you're putting electrons into the subtractive combination, into the anti-bond, you are effectively breaking that chemical bond because here there can be no electrons between the nuclei. So that's essentially the difference between the bonding orbital and what we call the anti-bonding orbital. So any questions on anything here? All right, so for us, the way we're going to make a molecular orbital diagram is we're combining orbitals from each atom to make the molecular orbitals, and that will be done for you because I'm going to give you the MO diagram. And when that happens, we're always going to get the same number of molecular orbitals produced as atomic orbitals used. When two atomic orbitals are combining, two MOs are produced. one will always be bonding and one will always be antibonding. So what that means is in any given MO diagram, you should always have the same number of bonding and antibonding orbitals. So if you've got 4 bonding, you have 4 antibonding. So what it says below is half of your MOs will be bonding and half will be antibonding. What we're going to do is add up the electrons for both atoms, and we could add up the total electrons, but what I'm going to tell you is it's easier for us to add up just the valence. So I'm going to go ahead and add valence in here. So add up the valence electrons for both atoms, and then you're going to start at the bottom of the MO diagram that I give you, and you're going to fill in each energy level, then proceed to the next higher energy level. So remember, only 2 electrons of opposite spins are allowed in each orbital. So for something like that, we're talking about arrow up and arrow down. So any questions on anything here so far? All right, so these MO diagrams can help us predict whether a certain molecule can exist or not. So we're going to look at the helium atom, and helium would be a 1s2. We could also say it has 2 valence electrons. So I'm going to go ahead and use the method that was described in those instructions earlier, and I'm going to add up my helium, just like I was doing a Lewis structure. Each of them has 2 valence electrons for a total of 4 valence electrons. Now it's optional whether you want to go ahead and fill in your electrons here, but what I definitely need you to do is the middle part right here, which is your MO diagram. All right, so we have 4 valence electrons. I'm going to start at the bottom, 1 and then 2. And remember, they always have to be of opposite spins. Now we move up to the next energy level. And I've now placed in all 4 electrons. So any questions on how we filled in that MO diagram? All right, so now to figure out if this molecule can exist, we're going to do something called calculating the bond order. And we actually did this a little bit in a previous chapter, and I told you we'd get to an actual calculation for it soon. And today is that special day. So the bond order is 1/2 of your bonding electrons minus antibonding electrons. When a bond order is 1, we're going to call that a single bond. If it is 2, we're going to call it a double bond. 3, a triple bond. 0 would be no bond at all. And it is possible to have a bond order that's a fraction, like 1/2 or 1/3. And that's what we would see if we had a molecule with resonance. All right, so let's give this a try. So we are calculating out our bond order. So 1/2 times bonding electrons minus what we call antibonding. All right, so in our case, 1/2 times bonding. And for the bonding, we are going to be looking at anything that does not have a star. So the star means it's antibonding. So if it's bonding, it doesn't have one of those. So this is a bonding orbital. So now up at the top, we see this star here, and that star represents this is antibonding. So before we do anything else, any questions on how I labeled the bottom 2 as bonding and the top ones as antibonding? By the way, antibonding are always higher in energy than the bonding, so you'll always see the bonding towards the bottom of your MO diagram and the antibonding towards the top of your MO diagram. Okay, So now what I'm going to do is I'm going to look at the bonding electrons. So if I zoom in here, there's 2 arrows, that means 2 electrons. I'm going to go ahead and color code this just so we can find it later. All right, then I go up to my anti-bonding, and I see that we have 2 electrons in here. So I'll put another 2 here, and I'll color code. Actually, all right, so now for our calculation, 1/2 of 2 minus 2 equals, and it equals 0. So what this is saying is our bond order equals 0. So when we're saying a bond order is equal to 0, what we're saying is that the bond does not exist. There is no bond. So the answer to our question here, can the He2 molecule exist, is no. And the reason it's no is because the bond order equals 0. Any questions on anything that we've done here with finding our bonding and anti-bonding electrons, filling in the MO diagram, or doing our bond order calculation?
It would be like 1s, and then the other 1s, and then 2s, and the other 2s, and then so on and so forth.
Yes, exactly. So when we go on to a molecule further down the periodic table, we would see the 1s bonding and anti-bonding. Here's the 2s bonding and anti-bonding. And then we start seeing the p's right here, bonding and then anti-bonding. Exactly.
Thank you.
You're welcome. All right, other questions so far about anything we've talked about? Okay. So MO diagrams kind of scare people, just like that horrible looking organic molecule I put on the screen earlier, but they're not so bad. As long as you remember that you're going to count up your valence electrons just like you were doing a Lewis structure, then you're starting at the bottom and you're filling up your MO diagram, and then for your bond order, calculating bonding minus anti-bonding, then dividing that by 2 or multiplying it by 1/2, and you'll always find the anti-bonding by that star right there. If it doesn't have a star, it is bonding. All right, so questions on anything here? All right, so here it says what is the MO diagram for O2 and what is a bond order for O2. Now the first thing I'm going to do is I'm actually going to cross out the bottom part. So I used to go into detail to prove to everybody that you can either use your full electron count or your valence electron count, but by the time I did it both ways, students would start getting confused, and on the test they didn't know which way to do it. So I'm going to stick with the valence electron. Those of you who are like, no way, I want to do the full electron count, you can definitely do it, but that MO diagram that I'm going to be giving you, and let me actually show you what that is, and you're going to see the exact same one in your homework, and you will get this identical one on your exam. What you're going to see is they start with the 2s. So they're already set for valence electrons, because I think this is a much easier approach. But anybody who's like, oh my god, that's horrible, I want all my electrons in there, come talk to me and I'll see if we can work something out. But most people are not interested in doing the full electron count. And this is much easier doing only valence. All right. So here we have our 2 oxygens. And anyone remember how many valence electrons in an oxygen? Excellent, 6. So we got 12 valence electrons. All right, and then what I mentioned earlier is the only thing I need you to do is the middle part here. If you want to go ahead and do the rest, you can. So I'm going to go ahead and fill in just the MO diagram. So we have 12 electrons to place, and I'm going to start right down here at the bottom. So I'm going to go 1, 2, and then I move up to the next level, 3, 4, 5, 6. And now notice you have two orbitals at the same level. That's very similar to the way we did our p's. So let me just remind you how we did our electrons when we were doing just the electrons for one atom. So here for oxygen, we would have 1s2, 2s2, and I believe, let me double check my periodic table, sorry. Oxygen is the fourth one over. There we go, 2p4. And what we would do, we would put our 2 electrons in the 1s, the 2 electrons in the 2s, and then for the p's, we said 1, 2, 3, and then we came back for the fourth. So the idea is everybody gets one electron before anybody gets 2, as long as they're at the same energy level. Once upon a time, we call that degenerate. And I told you it's kind of like a buffet, that everybody gets to eat once before anybody eats twice. So that's what's going to happen right over here. These are degenerate orbitals. Not that they're bad orbitals, just that they're at equal energy level. So we need to fill them what we call singly first. So everybody gets 1 electron before anybody gets 2. Okay, I lost my electron count, so let's go ahead and count up. So 2, 4, 6, 7, 8. All right, now we go 9 and 10. I've still got 2 to go, but any questions on anything I've done, especially right here with filling them singly first and then going back and giving each one 2? All right, so now we come to the next one, and we got 2 left to put in. Can I do this? No. Excellent. Resounding no. Each orbital gets 1 electron before anybody gets 2. Now, just like we talked about before, it doesn't matter if they're both up. You can have one up, one down, or if you feel like it, there you go. You can have them both down, totally up to you, as long as you have 1 in each orbital. I'm going to go ahead and just put mine up for the heck of it, but if you choose to put them going down, nobody will judge you. Nobody will even know. Can they go to the box above those? They cannot go up there until we have fully filled this one. Once this is fully filled, then we can move up. So the idea here is that we have to move up sequentially. So you can't skip anything and you can't jump ahead. So you just have to go slowly and progress through. Just taking one step at a time. All right, so questions about anything we've done so far? All right, so now let's do our bond order. All right, so we said bond order is 1/2 of, the bonding electrons minus the anti-bonding electrons. So we're going to hunt, okay, so why does it start at the 2s instead of the 1s? And that's because we're doing the valence electrons. If we did all of the electrons, then we would start right over here with that 1s. So in that case, we would have an extra 4 electrons, and they would fill up this area right here. But the idea of the valence electrons is the core will be completely filled, which means for every bonding orbital, you will fill an anti-bonding orbital, and they will cancel each other out. So that's why we don't need those core electrons. Does that help a little bit? Because I'm going to give you the orbital diagrams that you need. So I'm going to give you these right here, and they're already set for valence electrons. So you'll just start at the bottom. Okay. Yeah, so it's not up to like worrying about which level to start at, because I will the one I give you, you're always just starting out at that bottom level. All right. So here we're going to do bonding minus antibonding. And I think last time I did bonding in green. Okay. All right, so let's go through and let's find our bonding electrons. So the one that's on the screen right now, is that bonding or antibonding? Excellent. Excellent. So that'll be bonding, so I'm going to color that in green. How about that one on the top? Bonding or antibonding? Excellent. Your parents would be so proud you know how to spot your orbitals. All right. How about the one that's here in the center of the screen? Is that bonding or antibonding? Someday you'll be taking your kids for a walk and you're like, hey, 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 don't get near that one. That's an anti-bonding orbital. All right. So what about this one right here, this pi 2p? Is that bonding or antibonding? Excellent. How about this one right over here? Is that one bonding or antibonding? Excellent, antibonding. All right, so now what I'm going to have you do is I'm going to have you complete your calculation. So you are going to do 1/2 of the bonding electrons, which I've colored in green, minus the antibonding, which I've colored in purple right here. Let me zoom in here. Best I can. There we go. All right, so I want you to take a minute to count those electrons. So 1/2 bonding minus antibonding. And the AB is just an abbreviation for antibonding. Excellent. I see lots of bond orders of 2, and Jervin is recognizing that a double bond is what that means, and Tasso as well. Excellent. All right, I went ahead and put up the poll again, so go ahead and click in if you would like some more time on this one. All right, so looks like everybody who is voting, oh nope, we do have a couple people who want some more time. So let's go ahead and take another minute or so. Anybody have any questions about what we've done so far with our molecular orbital diagrams? Okay, so let's go ahead and give everybody another minute or so. All right, so let's go ahead and work this one out together. So first bonding electron, so let me zoom on in. So I see 2, 3, 4, 5, 6, 7, 8, and it looks like we had 8 bonding. And anti-bonding, it looks like we had 2, 3, 4. So 8 minus 4 is 4, divided by 2 will give us 2, so our bond order is 2, which predicts a double bond. And that is correct. Oxygen is a double bonded molecule that looks something like so. So any questions on how we got our bond order or how we did our molecular orbital diagram? All right. So first off, I'm going to cross off this bottom part because we're going to deal with valence electrons. Next, let's do our valence electron count. So we have 2 oxygens. Each one would be 6 valence for a total of 12. But we have to deal with this -2 there. What do we do about the -2? Do we add 2 electrons or do we remove 2 electrons? Excellent. We are adding 2 electrons for a total of 14 valence electrons. All right. Any questions on anything there?
The sign only refers to the valence electrons, right? Not the core electrons.
Yes, we are going to do strictly valence electrons. You could deal with the core, but you don't need to, and I think it's easier if we just stick with valence. All right, so now I know the picture might be hard to see depending on your device, but we said we had 14 valence. So do your best to fill in your 14 valence electrons into the MO diagram, which again is the center part here. All right, you're a little ahead of us, Dervin, but good work. So when you guys do finish this, feel free to go ahead and do your bond order. And you can see if you agree with Dervin, who thinks it's going to be a single bond. And it looks like Juan agrees. Excellent. And it looks like Ali agrees as well. All right, and Andrew agrees as well. Excellent. And Tasso? All right, so it looks like Kim got something similar. All right, so I went ahead and launched that poll, so go ahead and click in if you'd like more time. Are you ready to go over it? So it looks like I've got a couple people who want some more time, so let's take another minute or so. See, question, is it ever possible to get a negative result? Do you mean for the bond order? Okay, so no, you could never get a negative because 0 is the lowest. 0 says no bond. I guess I should say maybe in theory, maybe like if you tried to make a helium-2 negative, in that case you could theoretically get that, I suppose. Okay, I'm going to say theoretically, yes. Not on any real problem that I would ever give you, but if you were to kind of make up a crazy problem. But I would never give you one that would be negative, and in the real world, there would never be a negative one. All right, so let's go ahead and do this together. So we have 14 valence electrons. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so we've just done 14 valence electrons. Now we're going to do our bond order. I'll go ahead and put it right down here. So bond order equals 1/2. And I'm going to count up the bonding first. So here looks like I got 2 electrons. Now 4, 6, 8 electrons. It looks like we have 8 bonding. Now I'm going to look at anti-bonding. It looks like we have 2 right here. And it looks like 4 over here for a total of 6. All right, so 8 minus 6 will give us 2. Half of that will be 1. So we do indeed have a bond order equal to 1. If you were to look at the O2 2 minus, this is actually a polyatomic ion called peroxide. It looks like so. It is definitely single bonded, and it is a weak single bond. So if you've ever had, well, most of us have had peroxide, so you had it like poured onto your cut if you got hurt, and you see all those bubbles forming. That is actually this hydrogen peroxide degrading. That's that single bond breaking, and then it goes on to form O2 in the reaction. But this is definitely a single bonded molecule, just like the MO diagram predicts. All right, so questions on anything here about how we counted valence electrons, how we filled in bonding versus anti-bonding molecule orbitals, and the bond order? How's everybody feeling about molecular orbitals so far? Does this seem possibly doable come, I don't know, Monday? Better. Okay. Excellent. Excellent. Good, good. And your homework will give you a chance to practice. So these seem really scary when you look at them, and I know some of the YouTube videos, it's kind of mind-blowing, but they're not as bad as they look. All right. So here you're going to do F2, and again, I'm going to go ahead and cross out that bottom one. You're just going to do the valence electrons, but I want you to give this a try. So again, you're doing F2. Let me zoom in so you can see the picture. And I'm sorry, it's F2 2 plus. All right, so I want you to do the MO diagram and then find your bond order for F2 2 plus. That is it, yes. Jordan, I think you like these MO diagrams. Aw, I do too, Jordan. What's not to love about MO diagrams in science? All right, so I hear Andrew saying they've got a bond order of 2, and Clinton looks like you got the same thing. All right, so let's take a couple more minutes and we'll go over it together. All right, looks like Allie's getting a 2 as well. Excellent. And I agree, Jervin. It's very satisfying once you start to understand what's going on and it all makes sense. And it looks like Juan and Kimberly also got a double bond. Excellent. All right, I went ahead and threw up that poll, so go ahead and click in if you're ready to go over it or if you'd like some more time. All right, so let's go ahead and take about 1 more minute, and then we'll go over it together. All right, so let's go ahead and give this a shot. So I'm going to start by counting up our valence electrons. So each fluorine has 7 for a total of 14, but then we have a +2 charge, which means we got to take 2 away and make it 12 valence electrons. Any questions on how I did the valence electron count? All right, so now let's go ahead and fill in. I'm going to start down here and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And can I say 11, 12 like so? Jessica's the only one brave enough to tell me no. All right. So it should be like so, right? 1 electron in each box. Excellent. Oh, a Tasso as well. Excellent. Thank you, Jessica and Tasso. All right. Any questions about the 12 valence electrons or how I filled in here? All right, so we're doing our bond order. 1/2 bonding minus anti-bonding. So it looks like bonding, we've got 2, 4, 6, 8. So 8 minus 2, 3, 4. And 8 minus 4 will give us 4. Divide by 2 will give us 2. So we have a bond order of 2, which predicts a double bond. All right, questions about anything we did for this problem here? All right, so the next thing I want to show you is about how the p orbitals can form a sigma bond. So we talked about that a little bit once upon a time. And before we said, well, they can do a direct overlap. Something like so. Oops, let me try to draw that a little neater. Like so. So we talked about their direct overlap like so, but there's another way to draw them that we tend to do when we're doing our molecular orbitals. And that is like this right over here. And I know it looks kind of like a piece of candy, but what we're thinking is back to that wave function, where if the lobes that are coming together have the same sign, and again, it's not a charge, it's just a mathematical sign. If they are the same sign, then it's the additive combination, and it gets larger here between them. But if they happen to be at opposite signs, and they come together, that is when we get our node that goes right down the center. And remember, the node has no electron probability. So the antibond is when they had opposite signs coming together, and the bond is when they had the same sign coming together. So the bonding orbital has lots of electron density between the nuclei, And the antibond, we see a complete lack of electron density, essentially no electron density in the center between them. So any questions on this one right here?
Can you tell on which side of the red orbital on the left? How can you tell which side is like positive and which side is negative?
So I'm just assigning them as sort of random right now. So you would have to do an experiment to tell. But what we can tell from the bonding is that they must have the same sign. So they could both be positive, or they could both be negative. That's all we can tell from looking at this right here. Yeah. All right. So there is another way for them to overlap, and that is doing the sideways overlap that we see from our pi bonds. So we've talked about our pi bonds a little bit, and last time we talked about them, I kind of drew them like so. But with our molecular orbitals, we just draw them a little differently, but they still mean the same thing. It's still a sideways overlap, but here it looks like kind of two oval-shaped balls on the top and the bottom. That is the same as this over here. It represents the same thing. But the bonding is, again, when we have their signs lined up. And it really doesn't matter which ones, if the top is the negative and the bottom is the positive or vice versa. All that matters is that when the signs are lined up, this is when we get the additive combination. And when the signs are misaligned, so if instead I have a negative and a positive, they do not want to get together, and that's when you see the node right down the middle. So any questions about this being our pi and our pi antibond? When the signs are aligned, then we get the bonding, and when the signs are misaligned, when they're opposite, then we get the antibonding. Okay. All right, so there is another way to have the pi bond, and we saw this once upon a time, and I'm going to attempt a poor drawing of it. So here was our triple bonded molecule where we had orbital on the top and the bottom. We said electrons could go between them, but we said for a triple bond we have another set of orbitals, and here we have one orbital kind of going back. This is like into your computer and one coming out of your computer straight at you. It is my attempt for three-dimensionality here. So what we're looking at now is we are looking at the purple one. So they are trying to draw three-dimensionality right here. So I know when you first look at it, it looks like the middle piece is missing, the node is missing. It's not, it's just kind of on its side, going away from you and coming out towards you. So it works the same way as the last one, where this lobe is just coming out towards you and the one behind it is going away from you. And same thing over here. This is your antibond. It's got the node right in the middle. It's just, again, showing a different orientation. If I was there with you, I would show my iPad like so, and then leaned over on its side. So that's all they're showing you. They're showing you this image, now flipped over on its side. For me, when I look at these, they don't really look like the same orbital. But I know for people who are better at three-dimensional drawing, they tell me, yes, this is the way we draw in 3 dimensions. All right. The questions on anything so far? Let's see. Yes. So Jervin's bringing up a really good point. And he's saying it's odd because normally positives and negatives attract. But those are actually positive and negative charges. And these are signs. So let's say you're in math class. So if you're in math class and you have a positive 5 and another positive 5, you're going to get positive 10. But if you have a positive 5 and a negative 5 and you're adding them together, now you get a 0. So when you're thinking of the attraction, it's between a true charge, positive charge, and negative charge. But here, I want you to just think of it as sign as if it was in math class. All right, so any other questions or thoughts on this one? All right, so we can do MO diagrams with other molecules where we don't have two of the same atom. And here we have NO as an example. So let's go ahead and do this one together. And this one, I went ahead and started it at the valence electrons. So nitrogen is 5, oxygen is 6, for a grand total of 11. And those of you who watched your Lewis structure videos, like I hope all of you did, you may notice right away this is a radical. And by radical, I don't mean it's super cool and it can skateboard. I mean that it has a lone electron. It has an unpaired electron, which makes it a highly reactive compound. But let's go ahead and let's start adding these in. So we have 11 to put in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That is the odd electron that makes it a radical. It is unpaired and it also is an uneven number. Any questions on what we've done so far? Yes, and it is going to have a fractional or a decimal bond order. And Tassa, what do you mean by we're including the molecule? Oh, here I had already cut out the other. So on the other ones, I had another one drawn in here. Try drawing that a little nicer. So this one was in the other ones, and I had already cut that one out. No worries, you don't have to be sorry. Then it sounds like one had the same question. So this one is the one that we would have cut out. But remember, I'm going to give you the correct MO diagram, so you don't have to worry about cutting anything out on the homework or on the test. Okay, so let's do our bond order. So 1/2 bonding minus antibonding. So it looks like we have bonding, bonding, and bonding. So 2, 4, 6, 8. And here's for the antibonding is 2, 3. So, oops. So I agree, it is going to be 5/2 or 2.5. So that 0.5 shows that there's one electron that does have some amount of resonance going back and forth between whether it's going to be on the oxygen or whether it's going to be on the nitrogen. All right, so any questions on how we did this one or any other one of our MO diagrams? All right, so in some molecules, the pi 2p and the sigma 2p are switched, but I will give you these two sets of molecular orbital diagrams, and right underneath you will have which elements they belong to. So you'll know which one to use by looking at the instructions here below. And you're going to see an exact set of this on the homework, and you'll also see an exact set of this as a handout for the exam. So any questions on anything here? All right. So the best part of MOs is that you're given the diagram, and what you need to do is fill up that diagram and then answer questions about that diagram. So it has to do with the energy levels and an interaction that happens between the 2s and the 2p orbitals. I'd have to take a look and see what the details of those interactions are, but yeah, we just have the 2s and the 2p start having an interaction, but again, I'd have to take a look and see what exactly that interaction is. All right. So next up, I promised you we'd talk about paramagnetism and diamagnetism. Oh, in this case, will you fill the anti first so long as it's above? So you are always filling the bond. You're just going in order, and you're always filling bonding before the anti-bonding. And so the difference would be here you fill the pi 2p, sigma 2p, and then you get into the pi antibond and then the sigma antibond, whereas in the other one, here we have the sigma and then the pi, and then we have the pi antibond and sigma antibond. So the real difference is just these orbitals here get swapped. But we're still going from bottom to top, and we're still always filling the bonding before the antibonding. So other questions so far? Okay, so back to our paramagnetic and diamagnetic, and you've seen this slide before. And oops, that little boy waving represents the arrow. And here we have paired electrons. So the paramagnetic actually means unpaired. You have at least one that is unpaired. Diamagnetic means that it's going to be all paired up. So I know we looked at this before when we were doing our electron configuration and orbital diagrams, but any questions on anything here? All right. So what I'm going to have you do is give this a try. It says how many unpaired electrons are in O2 and F2, which are right down here, and I'll zoom in so you can see it better in just a moment. And then we want to know if they are diamagnetic or paramagnetic. So let's see if I can zoom in. All right. So how many unpaired in each one? And you're going to decide if they are diamagnetic or paramagnetic. All right, so Jessica is saying that on the left would be the para, and then it looks like Jervin says para on the left, dia on the right. And Clinton is saying that O2 has 5 paired and 2 unpaired, and it's para. And Kimberly has 2 unpaired and paramagnetic for oxygen. And Jessica is saying that F2 would be diamagnetic. It looks like Kimberly has F2 as 0 unpaired and diamagnetic. Excellent. All right, so go ahead and take one more minute on this, and then we'll go over this together. All right, so go ahead and click in if you'd like some more time or if you are ready to go over this. So go ahead and take about 1 more minute. While you're working on that, I'm going to try to pull up this YouTube video. Not working. There we go. All right, let's go ahead and go over that. All right. So starting off with our unpaired electrons, on the oxygen we have 2 unpaired electrons. And for fluorine we have no unpaired electrons. So any questions on why we said that our oxygen would have 2 unpaired electrons and the fluorine would have no unpaired electrons? All right, so next up for the oxygen, it would be paramagnetic because we have those unpaired electrons. And for the fluorine, I'm going to call it diamagnetic because everything is paired up. All right, so any questions on how we labeled these paramagnetic or diamagnetic, or how we counted or how we determined the number of unpaired electrons? So if I was to ask you the magnetism in a molecule, is it paramagnetic, is it diamagnetic, you need to draw the MO diagram because there's no other way to tell other than the MO diagram for a molecule. So any questions on anything there? Okay, so we're almost done. So here is just a representation of what we call a gooey balance, and it's a balance where we can actually determine the magnetism. So what we do is we hang our sample basically into a magnetic field, and over here is just a balance that counterweights it, and this is showing an old-fashioned one. Of course, the newer ones are electronic. So I see a question from Andrew. Give me just a moment. So the newer ones are electronic, and you don't have the actual little weights over here. You would just insert your sample, but here we can actually see what's going on. So what happens is once you turn it on, the field is applied. So it's a magnetic field. And if you have a diamagnetic sample, it starts moving out of the field. So essentially, it looks like it is lighter. It appears to have a lower mass. And what the balance does is that calculates how much magnetism it must have based on how much it moved when that field was on. Over here, if it's paramagnetic, it's actually drawn down into the magnet, and it seems like it's heavier. And again, once it calculates how heavy it was in the beginning versus how heavy it is after it's drawn into that magnetic field, then it can determine the magnetism of it. Sorry, my brain was on Andrew's question. It's so hard for me to leave a question unanswered. All right, so when we're doing the electron configuration, that's for an individual atom. So let's say I asked you for unpaired electrons in oxygen, just standard old oxygen. 1s2, 2s2, 2p4. So this is where you would do your electron configuration, your orbital diagram. And now you could say one oxygen all by itself is paramagnetic and has two unpaired electrons. But if I asked you not for oxygen, but in O2, it's a molecule, now you need the MO diagram. Does that sort of make sense why you would need the MO diagram for O2? Okay, excellent. So I got one more thing for you. I always forget that I can't click on a PDF in my iPad to bring the YouTube video up. So, and yes, there are two unpaired electrons right here. So let me go ahead and bring that video up in another way. It's a fun video. It's worth the wait.